Welcome to our next lecture in Elementary Statistics, Math 1342 at Dallas College with Professor Michael Bailey. We're looking at Chapter 4, Section 4, Methods of Counting. We're going to look at how to count the number of ways a sequence of operations can be performed. Then we're going to look at different types of counting, permutations, or combinations, and we'll explain what those are and then figure out how to do those countings for different scenarios. So before we start, try a little exercise here. How many ways can you travel from town A to town C by passing through town B using the diagram below? You can think of each of those lines as a road. So how many ways could you actually go from A to C passing through B? Well, there's three roads from A to B, so there's three ways to get to B, and then there's two different ways to get to C. Some people might have thought five, but it's actually a product. It's three, because think about it like our tree diagrams we saw before. We could go A1 or A2, B1 or B2, and C1 or C2. If an operation can be performed in n number of ways, and a second operation can be performed in n number of ways, then the total number of ways to perform a sequence of two operations is the product, m times n. In general, if a sequence of several operations is to be performed, the number of ways to perform the sequence is found by multiplying together the number of ways to perform each of the operations. I think I've just said the same thing three different ways. So try this one. A certain make of automobile is available in any of three colors, red, blue, or green, and comes with either a large or small engine. In how many ways can a buyer choose a car? Again, we have three colors and two engines, so we have six different possible choices. Again, we could have red large, red small, blue large, blue small, or green large or green small. So in these smaller examples, hopefully that's helping you kind of see that that is a logical or intuitive kind of thing to figure out. Let's try another. License plates in certain states, in a certain state, contains three letters followed by three digits. How many different license plates can be made? Again, hit pause and see if you can figure this out. Well, notice here we actually have six different choices, not two, but six. So if you originally did 26 times 10 and got 260, that's not correct. Sometimes making a hangman style game with each of the choices. Notice we have 1, 2, 3 letters, 1, 2, 3 numbers. Well, how many ways can we pick the first letter? How many letters in the alphabet are there? There's 26. And license plates can have repeating letters. So for the first three places in our hangman chart, we have 26, 26, 26, different ways of choosing them. Again, this is a product. And then how many digits there are? Well, 0 through 9 is 10 digits, so the last three choices are 10 digits each. So when we multiply all of these numbers out, 26 cubed times 10 cubed, we get 17,576,000 different license plates. It's shocking how quickly the number of possibilities happens, even in a small thing like this, that, you know, with just a 6-digit license plate, alpha and numeric, we have over 17 million different possibilities for a license plate. So here again, hit pause and try these two problems. The first one's pretty straightforward. We're ordering a computer. There are 3 choices of hard drive, 4 choices of memory, 2 choices of video card, and 3 choices of monitor. So how many ways can we configure our computer? Pretty straightforward. 3 hard drives, 4 memory, 2 video cards, and 3 monitors gives us 72 different choices. Now be careful. In the second one, we have 3 true-false questions and 2 multiple choice questions with 5 choices each. How many different sets of answers? Well, since there are 3 questions with 2 possibilities each, you might think of just multiplying 3 times 2 and 2 times 5. Unfortunately, this would get it wrong. We have 2 questions. We have 3 true-false questions. So in this case, it's better to actually draw the hangman. Okay, so we have 3 true-false questions and then 2 multiple choice questions with 5 options. So this isn't 3 times 2. This is 2 cubed. This isn't 2 times 5. This is 5 squared. So be careful. This is a very common mistake that students make, just multiplying here because they know it's a product. But what they're really doing is they're adding them all. So put all your choices, how many choices there are. There are 5 questions. And then list the number of options in each of those and then multiply through. And so these are more about an exponential than simply a product. The word permutation is another word for ordering. And this is really important. A permutation is about an ordered number set. When we count the number of permutations, we are counting the number of different ways that a group of items can be ordered. For example, if 5 runners run a race, one of them will finish first, another will finish second, and so on. And how many different orders can they finish? Well, here order is important, and you can't just say, well, there's 5 people running, so there are 5 possibilities for first place and 5 for second and 5 for third, etc. And why is that? Well, think about it. As soon as you pick out of the 5 for first place, you've eliminated one of the runners from the race because they've already won. So now we have 4 choices for second place. Again, as soon as we've got first and second place, we only have 3 to choose for third, 2 for fourth, and 1 for fifth. Okay, so this is what a permutation is about, is that, when a different order has a different meaning, like if any of these people were in a different place, they would be very, especially if they move to the left, to the, first place, it has a different meaning. If I come in third, it's not the same as if I come in fifth or come in last. Okay? So we multiply these out and we get there's 120 ways for 5 people to race and have different orders of finish. There's something in math called a factorial, and this is written as you can see up here like 5 exclamation point. And what that means is you can write any number in front of it, an integer value, a whole number, n factorial. And this just means the product of each of the multiples down to 1. So for example, 5 factorial equals 5 times 4 times 3 times 2 times 1. Whereas 4 factorial would be 4 times 3 times 2 times 1. Okay? So again, this is kind of the definition. N factorial equals n times n minus 1 times n minus 2, etc., until you get down to the last possible digits, which are 3, 2, 1. Notice by definition we also include 0 factorial as 1. This is something, I don't know that we'll deal with it so much in probability, but we deal with it in other math. A lot of people think 0 factorial would be 0, which sort of makes some intuitive sense, but we've defined it. Again, we've made a law that this equals 1. Sometimes, and especially in probability, it's interesting to recognize how you can break factorials down. Of course, you can just break it down into all the digits that are being multiplied, or you can break it down into higher digits times a factorial. For example, 6 factorial, 6 times 5, 4, 3, 2, 1. Well, this is the same as 6 times, as you can see in parentheses, 5 factorial. You could also say 6 times 5 times 4 factorial. 6 times 5 times 4 times 3 factorial. This kind of breaking it down makes some problems that look really complicated much easier to solve. Sometimes we want to count the number of permutations of a part of a group. For example, 10 runners run a race. The first place finisher will win a gold medal, the second place finisher will win a silver medal, and a third place finisher will win a bronze medal. In how many different ways can the medals be awarded? Hit pause and see if you can do this. Again, you can use the hangman method, which we've been using. And we're going to also look at permutations. So how many different possibilities are there for first place? Well, since there's 10 runners, there would be 10, and then for second, there would be 9, and then for third, there would be 8. Okay, so I've just gone through that. So there's 720 different possible outcomes for this race. In the last example, the 3 runners were chosen from a group of 10, then ordered as first, second, and third. This is referred to as a permutation of 3 items chosen from 10. The permutation of 3 items chosen from 10 total, if you will. This is written as the permutation of n would be the total number, which would be 10, and then how many you're selecting. The permutation of 10 things taken 3 at a time. The number of permutations of our objects chosen from n is calculated by n factorial over n minus r factorial. So in our example, we had 10 runners, and we were looking for the first 3 places. So 10 minus 3 gives us 7 factorial. So again, you can see here why this makes it a little bit easier to calculate this. 10 factorial over 10 minus 3 factorial gives us 7 factorial. But we can break 10 factorial down into 10 times 9 times 8 times 7 factorial, and the 7 factorials simply cancel, giving us the 10 times 9 times 8. I want you to see in some of these processes, you want to use the permutation function, which you have on your calculator, by the way, versus the hangman, especially if there's a lot more spaces that you have to kind of fill up. If they're simple calculations, you can use kind of the hangman model and logic through it. On your TI-80 calculator, if you look under the math button and then go to prob, which is probability, and then go to number 2, you'll see the permutation just like this, and it will have places where you can enter the total number of things and the number of things that you are choosing. So let's try another one. 5 lifeguards are available for duty one Saturday afternoon. There are 3 lifeguard stations, and how many ways can 3 lifeguards be chosen and ordered among the stations? Again, it says that they're ordered, so that a lifeguard at station 1 would be different than a lifeguard at station 2, etc. So although you're creating a shift of 3 lifeguards, you're actually assigning them to specific stations, so each one is a little bit different, and so that's why the order matters. Again, see if you can do this. Hit pause and then come back. So notice here we are choosing 3 items from a group of 5 and ordering them. So this would be the permutations of 5 things taken 3 at a time, which is 5 factorial over 5 minus 3 factorial. Here you can see we've multiplied it out. The 2 times 1 cancels. We just get left with 5 times 4 times 3, which equals 60. Again, you could have done the 3-piece hangman, right? There's 5 ways to pick the first lifeguard, 4 to pick the second, and 3 to pick the third, as you can see here. So I want you to kind of see how to do this. It might be a good idea for you to try your calculator and see if you can enter it into the calculator. So it's always good when you're going through a long study grouping to take a breath, to get up, to stand up, go get a drink, step outside, take a little walk, something that can kind of keep you engaged. I'm not sure if this is going to work, but I'm going to try it. This is Mary Oliver reading her poem.
So this is Wild Geese. You do not have to be good. You do not have to walk on your knees for 100 miles through the desert repenting. You only have to let the soft animal of your body love what it loves. Tell me about despair, yours, and I will tell you mine. Meanwhile, the world goes on. Meanwhile, the sun and the clear pebbles of the rain are moving across the landscapes, over the prairies and the deep trees, the mountains and the rivers. Meanwhile, the wild geese high in the clean blue air are heading home again. Whoever you are, no matter how lonely, the world offers itself to your imagination, calls to you like the wild geese, harsh and exciting, over and over, announcing your place in the family of things.
Mary Oliver was the poet laureate of the United States at one point, and I love her poetry. I think it speaks to me about dreams and longing and struggles, and so this is one of my favorites. She has another one called The Journey, which we might get to see as well later on. But again, it's important when you're engaged in like some content that may be a struggle, that you do it in sizable pieces, and that you take breaks and pauses between work and education and everything. All right. So you can take a pause, go get a drink or something, and come back and then finish. We don't have much more. Next thing we're looking at is combinations. In some cases, when choosing a set of objects from a larger set, we don't care about the ordering of the chosen objects. We only care which objects are chosen. For example, we may not care which lifeguard occupies which station. We might care only that 3 lifeguards are chosen for a specific shift. Since we are just looking for a shift of 3, putting the named lifeguards in different order does not change the team for the shift. So I want you to see that in that same example, order may be important if we're really concerned with which lifeguard is at which station, and then it's different. If we're just saying we need a team of 3 lifeguards for all the stations, then it does change the way we count. For example, if we're just looking for a shift of 3, then our shift having Bob, John, and Sue is the same team as Sue, Bob, and John, just putting the names in a different order. When you have distinct group of objects that can be selected without regard to order, meaning that if you reorder them, it is the same group, then this kind of objects or this kind of experiment or example is called a combination. So like in permutations, Bob, John, Sue is different than Sue, Bob, John because the station was important. Here we're just looking for a shift, and so on the morning shift, Bob, John, and Sue is the same as Sue, Bob, and John, and that's called a combination when order does not matter. The number of combinations of our objects chosen from n is c combinations of the number of things taken r at a time, and we get n factorial over r factorial times n minus r factorial. So let's look at another problem. Whenever you see thinking at the top, this is a good time to stop the video or pause the video and try the problem on your own. See if you can work through how to do the problem. I try to include the formulas that you'll need here, but it really works better if you actually try this instead of just passively listen and watch. Okay, so maybe hit pause and try it. At a certain event, 30 people attend and 5 will be chosen at random to receive prizes. The prizes are all the same, so the order in which people are chosen doesn't matter. Remember before we saw people given different prizes. If you were first in the order you got the top prize. If you were fifth, you got the last prize, and so that was a permutation. When the prizes are all the same, it doesn't matter if you have 5 people in any order, they're all getting the same thing. So changing the order does not change the meaning, in this case, what prize they get. So how many ways can different groups of 5 people be chosen? So the first thing we might try is doing the hangman method. And so we have 30 ways to choose the first person. Once we choose a person, then we only have 29 left, etc. But remember, this hangman works mainly when you have permutations, when order does matter. That specifically we have 30 ways to choose the first, then 29 for the second, etc. So this is when order matters. So this process of using the hangman doesn't work for permutations. I'm sorry, only works for permutations, and generally not for combinations. Since the order of 5 chosen people does not matter, we need to compute the number of combinations of 5 chosen from 30. This is the notation for this, the combinations of 30 things taken 5 at a time. So we're looking for those groupings with no common groupings by order. So again, we plug this in. It's 30 factorial over 5 factorial over 30 minus 5 factorial. Let me get my pointer here, right here. 30 minus 5 is 25 factorial, so we have this in the denominator. And remember that whenever you have a factorial, you can break it down, you can factor it into lower factorials, every number below. This is 30 times 29 factorial, or 30 times 29, 28, 27, 26 times 25 factorial. So we can easily see we can cancel out the 25 factorials, and we're left with this simple product and ratio. And we see that there are 142,506 different ways or different groups of 5 people based upon just 30 of them. It is amazing the different combinations and permutations. Again, if we're doing permutations, it's even a much higher number. Again, notice if the prizes had been different, for example, a grand prize, a second prize, then this would have been a permutation of 30 things taken 5 at a time. Here we have another problem. Again, hit pause and see if you can handle this. This is a little more complicated. Notice the title, Mixed Counting. At a certain event, 30 people attend, and 5 will be chosen at random to receive prizes. There is a gold and silver prize for first and second. Third, fourth, and fifth place are all the same prize at 100. How many different groups of 5 people can be chosen? So notice that we have 2 different types of prizes here. The first 2 are different, so that's a permutation. Order matters. If I'm in second, I don't get the same prize as first. But if I'm in the third, fourth, or fifth position, they're all the same, and so it doesn't matter if I'm in third or fifth, I still get the same prize. So the hangman can kind of help us here if we think about this problem as 2 problems. Here on the left, we have the hangman. Let me get my pointer again. Here on the left, we have the pointer with 2 places, and then on the right, we have 3 places. So I first might be tempted to try this, 30 times 29, which remember works for permutations, but doesn't work for combinations. All right? So we need to be careful there. But it can help us figure this out. Notice for third, fourth, and fifth place, no matter the order, Ann, Bob, James, and Bob, they all receive the same prize. So these are not different groupings of those 3 prizes. So really what we're doing here is we're taking a permutation of 30 things taken 2 at a time. Now, why did the combination change? We're not taking the combination of 30 things 3 at a time. Because we've already taken out the first and second place, there's only 28 people left. And so that's how we organize this problem. And so we see there's almost 3 million different ways for 30 people to win 5 prizes, first and second, and then 3 same prizes for third, fourth, and fifth. It's kind of crazy, right? The TI-84 does permutation and combinations on your calculator. Again, your book has great instructional tutorials at the end of each chapter where we're doing different statistics, formulas, and processes using technology. So refer to your textbook or go and Google using a TI-84 with whatever you're doing, combinations, permutations in this case. Also in Excel, you'll have some Excel problems like this that you'll get experience in ALEKS. All right, so let's look at another problem. So how do we use this counting in order to make sure that our calculations of probability for events is accurate? So see if you can try this. Remember that the basic probability of an event is equal to the number of outcomes in the event divided by the number of outcomes in the sample space. So this is where the counting really comes in, because it helps us figure out how many possibilities there are when we have these special counting situations of groups of permutation or combination. So using this basic formula and what you know about combinations and permutations, try this problem. All right. A box of 10 light bulbs contain 8 good light bulbs and 2 burned out bulbs. 4 bulbs will be selected at random to put into a new lamp. What is the probability that all 4 bulbs are good? Well, the first thing we want to do is figure out the sample space. This is pretty straightforward. And again, remember in all of these, when you're trying to figure out is it a combination or a permutation, the first question you want to ask is, if I have a box of 10 light bulbs and I take 4 at random for a sample, if I move those in a different order in my sample, those 4 light bulbs, do I have a different sample? Am I testing a different set of 4? Samples like this, where we're usually testing for that they work properly or defects, or that there are no defects, samples are generally, when you usually see a sample, the word sample, we're taking a sample of 4. This generally implies a combination, because again, we're testing 4 out of the 10. If we move those bulbs around in a box or in order, it's not changing the 4 that we're sampling. So this is a combination problem as far as the ones that we're selecting. However, our sample space, right, we can, with 10 light bulbs selecting 4 at a time, again, we're not changing the order of the bulbs in the sample doesn't change the sample, so this is a combination problem. Okay, so we have the combination of 10 things taken 4 at a time. Then we need to figure out how many possible event options, and this is that we select only 4 good bulbs. So again, the sample spaces are generally the easier ones to figure out, and this is simply the combination of 10 things taken 4 at a time. So we get 10 factorial over 4 factorial times 10 minus 4 factorial, and that gives us 210 different samples that we could pull out of this box of 10 light bulbs, 4 at a time. But now we want to select 4 good bulbs. Okay, how do we select 4 good bulbs? Well, the question, when we're looking at this, we have to figure out how many good bulbs are in the original population. And so we're going back to that 10 a box of 10 light bulbs, and how many are good in there? Well, we can see from the problem that 8 are good. So we're just going to select from the 8 good light bulbs. How many different groupings can we select? And again, putting them in different order doesn't change things. So this is simply a combination of 8 good light bulbs, and we want 4. How many different combinations are there? And in this case, there are 70. Okay, so this is a really a true and thing that you have to pay attention to is the event. So since we're selecting 4 good bulbs, we can only select them from 8 because the other 2 are faulty. And if we put them in this, then we're not going to necessarily know how many different combinations include all bulbs being good. Okay, so our probability is just this number of event outcomes, 70, divided by the sample space, 210. So we have a 1 in 3 shot at picking out all 4 good bulbs. That's a pretty high percentage. That's a relatively 33%. So try these now and see if you can do these. Again, hit pause and see if you can figure out the different ways or probability. They're a little confusing, so think about it and take your time. A committee of 8 people must choose a president, a vice president, and a secretary. And how many ways can this be done? So we know that we're selecting from a group and we need 3 roles. Okay, again, our first question is always, how do we select those 3 roles? Once we select those 3 roles, if we put them in a different order, will there be a different grouping? And so when you're thinking of this like president, vice president, secretary, you can think of the first person selected, second, and third. So if I move the order around, let's say whoever's in first is president. If you're put in third, then you're secretary. So order does matter here. So this is a permutation problem, and we get 336. 2 of the committee members are Ellen and Jose. Assume the assignments are made at random. What is the probability that Jose is president and Ellen is vice president? This is a good place where the hangman works, okay? Because we have 3 choices. And so notice this says that we want Helen and Jose that Jose is president and Ellen is vice president. So in this case, our event space, how many ways can we pick Jose to be president? Well, there's only one way because there's only one Jose in the group, and there's only one president. Okay. The same with vice president. We want Helen to be the vice president, and there's only one way to pick this. So we have 1 times 1, and then how many ways are there to pick the secretary? Okay. There's 6 ways now to pick the secretary because there are 6 people left. So this is the probability of 6 things taken from our sample space of 336, and so we get a probability of 1 over 56. To me, probabilities and counting can be really helped in our thinking with the hangman, but you have to know the difference between when it works and when it doesn't work. Now let's look at this and change it up a little bit. What is the probability that either Helen or Jose is president and the other is vice president? Well, again, we can use this. So how many choices do we have for president? Well, if it can be either Helen or Jose, then we have 2 choices for president. How many choices do we have for vice president? Well, this is in an ordered fashion, right? So once we've picked the president, there's only one possibility for the vice president. So we're not going to put 2 times 2 times 6 here. It's going to be 2 because we have Helen or Jose for president, and then whoever is left for the vice president. And so here we have a possibility of 12 out of 336, again, our sample space, or 1 out of 28. And so you can see that basically the probability increases, it really doubles, okay? All right. Let's try 2 more. hit pause and try these. 8 college students have applied for internships at a local firm. 3 of them will be selected for interviews. In how many ways can this be done? All right, so we have 8 students and we're looking for interviews. Again, our first question is, if I select 3 people and put them in a different order, does that change the meaning? Well, we're selecting 3 of them for interviews. They're all getting interviews. It doesn't say there's anything different about this. So Bob Sue Ann is the same as Ann Sue Bob. Okay? So this is a combination problem. So we have the combination of 8 students taken 3 at a time. When we do this, we get 56. I'm not going through the computations. You can try those on your own. 4 of the 8 students are from Middle Georgia State University. What is the probability that all 3 of the interviewed students are from MGSU? This is very similar to the light bulb. So again, if you haven't hit pause, see if you can do it. So notice now of the 8 students, we want to select all 3 of them. Our event is that all 3 are from Middle Georgia State, okay? Well, there are 4 out of the 8 are from Middle Georgia State. Again, it's a combination problem because they're all getting the same thing. So the way that we figure out how many possibilities are there for 3 of the 4 being from Middle Georgia, then we take the combination of 4. There's only 4 students from there, so we have to pull from only those students because we're looking for all Middle State Georgia, taken 3 at a time. Okay, to calculate the probability, of course, this is our event, number of outcomes for our event. This is our sample space, the number of ways we can select 3 people out of 8. So our probability of selecting all MGSU students is 4 out of 56, or 1 out of 14. So we've covered all of these. Make sure, even using the language here, do you know what the fundamental principle of counting is? Do you know how to count the number of permutations of n objects? How to count the number of permutations of r objects chosen from n? How to count the number of combinations of r objects chosen from n? How to compute probabilities using permutations and combinations, and do you know how to figure out when it's a permutation versus a combination? These are very important. We've just done a couple exercises in here, so rely heavily upon Alex.